We have been running this. By the way, my name is Narasimhan, and we started this seminar Colloquium series 5 years ago. And we have been doing this with the help of a few other faculty colleagues and Linda Vida here and her staff members. In all these years, we somehow forgot about glaciers. We talked a lot about water and various aspects, primarily because we were, by and large, unless otherwise stated, we are interested in water because it is a commodity, it has money. But there are other beautiful aspects to water, and glaciers is one of them. And right now, glaciers are becoming a focus of attention for more than one reason. We have been reading in the newspapers that in the summers we may not have an Arctic glacier anymore. North Pole may be a lake or a water body. And because of that, it is very timely that finally we realize that we have not covered glaciers. And then when I looked around, I suddenly discovered that we have a brilliant glaciologist in our own midst here in the Berkeley campus. Glaciers are generally studied in the geology department, but Professor Cuffey is a professor of geography. And that is a very subtle difference in the approach to glaciers from a geological and from a geographical point of view. The subtle difference is the geography orientation towards glaciology is a little bit more slanted towards the connection to human beings, which essentially is the purpose of this colloquium, water resources in relation to humans. Professor Cuffey has done work extensively in Antarctica and other places. And his interests include not only glaciers by themselves, but also the relationship of glaciers to rivers and streams, ecosystems, and human beings. So we have been very fortunate to have a very distinguished, I may call, because of all my gray hairs, I may call him young. He has made quite a name for himself. A few years ago, the American Geophysical Union conferred on him the McElwain Award, which is awarded to the most distinguished young geophysicist under the age of 40. So we have a person who knows what he's talking about. With that brief introduction, I invite Professor Cuffey to give us a talk about glaciers in the California waterscape.
Thanks very much. Can everybody hear me? Is this a proper volume for this thing I'm wearing and all that? Okay. All right. I think it's good to first consider how I got roped into doing this by Professor Narasimhan. He suggested that I give a talk about glaciers in California, I think was the phrase you used. And I agreed to do so because being an academician, I can't refuse the prospect of a captive audience or a free dinner. So the combination of those made me say yes. But then after I said yes and sent the email, then it suddenly struck me that this is going to be a very difficult thing to talk about for the simple reason that there's almost no glaciers in California at all. And there are a few, as we'll talk about, but they're a very, very minor part of the California landscape. However, they do have a very large role in the global environment. Glaciers do worldwide, especially because of the role of the polar ice sheets in controlling climate and controlling sea level. So I'll talk a little bit about that. And there's another aspect of glaciers that's really important for the California waterscape, which is the Pleistocene legacy. That if you look back over the last 2 million years, California has actually been a fairly glacial sort of place. And there's all kinds of consequences for this. And what I'll do is just mention a few of these as we talk along. So then after I procrastinated for several months in the usual academician's fashion, and then I got back in touch with Nari, and I learned two things from my discussions with him. The first was that you are all very intelligent people, and you don't mind if I talk about glaciers in the California waterscape through indirect connections right? So you're all thoughtful people. So we don't need to have a big ice sheet sitting on Stockton to talk about glaciers in California. The other thing Narasimhan suggested or advised me on is he said, make sure you avoid cliches. So I thought about that for a minute, and then I said, sure, fine. And then later I was thinking, well, why in the hell should I avoid cliches? I mean, cliches may be, in fact, the most important part of the story. And furthermore, California is a place that's just driven through with cliches, right? I mean, the whole state is a cliche. Berkeley is a cliche. If you don't believe that, you should go to Texas and talk to somebody about Berkeley. So I'm actually going to reject your advice, and we are going to do some, I would say, unseemly embracing of cliches in this talk from time to time. And finally, the last introductory comment I'd make is that, there's a lot of the connections that I want to talk about are really forming a complex web. So the way that I choose to take you through this web may seem a bit meandering, because of course it will be meandering, because it's a web, and given the linearity of time, I have to take you through it. So glaciers. First of all, let me just say a few words about glaciers. Can everybody see the screen all right? I think it would be better if we could dim the lights a bit more. You get glaciation whenever a basic condition is met, which is simply that over the course of a year, you have to have a net accumulation of ice mass, of snow mass on the landscape, and which of course happens in cold places. And if such a condition of net accumulation over the course of the year, thank you, persists from year to year, what will happen is you build up an ice mass that's a glacier. And in principle, you can think that you'll build up this ice mass and build up an ice mass, and it'll get taller and taller and taller until you reach the top of the atmosphere, and then you've got these big towers of ice, and that's pretty remarkable. But in fact, glaciers have a remarkable property, or I should say water ice has a remarkable property. Everything about water in its physical properties and its role in biology is really remarkable. And one of the remarkable properties of ice is that even though it's a solid, it's essentially a rock. It's the rock of water. Despite that, it's viscous enough that on human timescales of years to decades, we can see it flowing. So glaciers engage in slow viscous flow. Let me just show you a few pictures of a really nice glacier. This is a glacier that I've been studying in Antarctica with some of my wonderful graduate students, including Andy Bliss, who's sitting back there. This is Taylor Glacier. It's an outlet of the main East Antarctic ice sheet. And if you stand right here where I'm taking the picture, you're standing on about 800 meters of solid ice. You have to go down 800 meters before you hit bedrock. And it's flowing off the main ice sheet down through this spectacular mountain landscape. This is what it looks like in map view. Here's a satellite image of the same glacier. The main East Antarctic ice sheet is over here, and it flows down like this around and then terminates in the dry valleys of Antarctica. And the total distance here is about 80 kilometers that you see in the plot here. So this is a very, very big feature. And of course, it's connected to the continental scale ice sheet. All of these red dots on here, it's not some horrible disease that the glacier has. It's instead the locations of the survey grid that we use to study the glacier. So if you look at those positions, then I could show you how fast the glacier is flowing at those positions. And a map of the flow vectors looks something like this. There's this big bend in the glacier right there. And here's a map of the flow vectors that show you how the glacier is flowing like so. So the flow of glaciers is something that's, although it's a process akin to much slower geologic processes like movement of the tectonic plates, it's something that's happening on a human timescale, and we can actually measure it. The next thing I'd like to mention is, or have you think about, is that a glacier is really just acting as a conveyor. It's acting as a conveyor for mass in the same way that a river acts as a conveyor for mass, transporting runoff across the landscape. In the particular case of glaciers, because the glacier is a solid body, what it's doing is it's transporting mass from some region where there's net inputs to the system, which we call the accumulation zone, and then the flow moves it to some other region where there's net output from the system, which we call the ablation zone. So here's up on the board here, I've got a little simple diagram. That's a glacier. There's inputs, which we call accumulation, and flow transfers that mass to outputs. And the input regions and the output regions are geographically distinct. That's an absolutely important thing to realize. The input regions are places that tend to be colder and hence higher elevation or further toward the poles rather than the equator. Or they tend to be the interiors of continental regions in the high latitudes. Whereas the output regions tend to be lower elevations that are warmer, or they tend to be closer to the equator in warmer regions, or it's the ocean where the glacier flows and makes icebergs. And glaciers change over time. This conveyor system is able to change over time, and it's pretty easy to think about the factors that make it change. You can increase the inputs to the system. You can have more snowfall. That would cause the glacier to grow. You can have increased outputs, which would mean increased melt, increased iceberg production. That would make the glacier shrink. And you can also play with the flow. You can make the flow easier by making the glacier warmer or the base of the glacier wetter for various physical reasons that I won't go into. If you increase the ease at which the glacier transmits its mass, then the glacier will shrink, all else being equal. And here's the more precise way of looking at it. I won't bother to talk about it except to say that if you consider a column going through the ice of some thickness I, then the rate of change of I over time depends on how fast you're adding mass to that column, which is the connection to climate. You're either adding mass by snowfall or removing it by melt. And then there's a flow divergence that's how much mass you're removing from that area. So that's the 5-minute introduction to glaciers. If you understand everything about this little equation here, then you know everything there is to know about glaciology, and the science is done. Of course, there's a lot of devil in the details of what's there. So what I'd like to do now is shift away from Antarctica, where we have these giant continental scale glaciers, and talk about California. And the first thing I'll do is simply tell you about the glaciers that we actually have right now in California. Although they're very small, they're really quantitatively, they're trivial in terms of area and volume. So they have a minimal effect on the climate of California. They have a minimal effect on the hydrology of the state. And this is in contrast to many parts of the world, especially the polar regions where glaciers are a huge component of the landscape, and kind of fringe polar regions like Iceland, let's say, where they're a large component of the landscape and there's people living in proximity to them. I was most impressed back in the mid-1990s. I went to Iceland for a few weeks, and I woke up one morning in Reykjavik and I looked at the morning newspaper, and on the front page there was a story about how one of their glaciers had just done something interesting in its flow. And I thought, yes, that's the sort of place I would like to live, where I'm sure as I walk down the streets, people would say, ooh, there goes a glaciologist. Okay. But in California, it's not like that. Not at all. They're quantitatively trivial in area and volume. But nonetheless, they are striking features. I mean, if you go locally and look at them, they're really interesting parts of the landscape. And the rarity, their small size actually gives them a sort of value that they wouldn't otherwise have. In a way, you could think about it as the glaciers of California are really just existing on the very edge of where it's possible for them to exist. And that gives them a different sort of value. They're just hanging out at the extreme edge of viability. So let me give you a quick run-through of the glaciers of California. The largest glaciers in California by far are the glaciers on Mount Shasta, the volcano in the northern part of the state. Here's a topographic map of Mount Shasta. You can see the concentric contours showing the conical form of the volcano, and I've helpfully outlined in blue the 4 main glaciers on it. The longest, here's a scale, the longest is about 2 miles long. And these are by far the biggest in California. And you can actually see these if you want. You drive up to the appropriately named town of Weed, California, and you drive east on US Highway 97, and there's a beautiful view of the glaciers. And if you sort of put on the blinders and look at those glaciers up on Mount Shasta, you can sort of pretend that you're in a real alpine environment if you ignore the smell of the sagebrush around you. But they're wonderful, wonderful things. And notice that they're on the north side of the mountain. There's a few little ice patches down here, but they're on the north side of the mountain because there's less direct sunlight hitting the north side of the mountain because we are in the northern hemisphere. And that's the only place that these glaciers can survive. There's also glaciers in the Trinity Alps, some very, very small glaciers in the Trinity Alps to the west of Shasta. I won't really say much about them other than to say that they're really, really small. And then there's lots of little tiny glaciers dotting the crest of the High Sierra. And this is just a road map of California. Here's Yosemite National Park and Kings Canyon National Park. And if I were to show you where all the occurrences of glacial ice are in the state, there would be little dots all over the high crest of the Sierra here. Here's the Central Valley. Here's Owens Valley, for those of you who need to be oriented. The most prominent glaciers, the most interesting ones by virtue of their size and role in the landscape, are the ones that are just 7 glaciers that I've indicated here in blue circles. So there are few enough of them that I'll just talk about each of them individually a little bit. First, starting at the north end, just north of the Tioga Pass Road, there's one on the north side of Mount Conness, which is appropriately the Conness Glacier. And this is an interesting glacier from a number of perspectives. Although it's very, very small, its total length is a bit less than a kilometer. It's the most accessible glacier. You all could visit it with about a 5-mile hike. Here it is. It's sitting, this is one lobe of it. There's another lobe back here. It's sitting just hiding on the north-facing slope of this basin, scoured into the side of Mount Conness. And then in front of it, there are these big ridges of rubbly material, which is moraine that was deposited by the glacier when it was bigger in the Little Ice Age about 1.5 centuries ago. If you then go closer to it, and close enough that you can actually see what it looks like better, this is what it looks like. Here's that cliff, the granite cliff, and then here's the glacier flowing down this way. And you can see there's some crevasses in it. There's artensional cracks that have been opened up by the flow. So you know it is flowing. And so it's acting as a little conveyor moving accumulated snow from up here in the top part of the glacier down to the lower part of the glacier where it's melting away. Now, one of my other wonderful graduate students, Johnny Sanders, is interested in these little glaciers, and we've got a project to study them. So he was actually just up at this Conness Glacier doing flow measurements, and apparently he found it to be very cold up there last week. Was it just last week? And here's some of his data. Here's the glacier seen in satellite view, and here these little vectors are flow vectors. So it too, just like Taylor Glacier in Antarctica, it too is moving. It's viscously flowing, but the rate of motion is modest. It's just a few meters per year. All right. So that's Conness Glacier. Then moving south, the next glacier of note is in Yosemite National Park itself. This glacier right here, actually it's a pair of glaciers on the north side of Mount Lyell. And it's one of probably the most aesthetically pleasing glacier. It's, of all the glaciers in the Sierra, it looks most like one would want to see in a classic alpine landscape sense. In fact, if you read John Muir's writing, there's this one passage where he talks about meeting some artists who came to Yosemite Valley, And they were kind of distraught because everywhere they looked in the High Sierra, all they saw was these vast rocky landscapes. But they had in mind this preconception that they wanted something that looked like the Alps, where they could go and paint this big canvas. And so they met John Muir, and he said, well, why don't you go up and I'll show you the Mount Lyell Glacier. So he took the artists up there, and they were suitably impressed. And this glacier feeds into its meltwater feeds into the Lyell Fork of the Tuolumne, which then it provides runoff for Hetch Hetchy Reservoir and hence San Francisco. So if you drink from any of the water source or water systems that tap into the Hetch Hetchy system, you're drinking some molecules that have melted off of Mount Lyell. There's an interesting historical thing about Lyell Glacier that I've seen in a number of books, and I remember seeing this a long time ago. This is a bighorn sheep, a Sierra Nevada bighorn sheep carcass that's actually melted out of Lyell Glacier as the glacier has flowed and conveyed particles to its front. And these sheep are extinct from the Yosemite region. They went extinct in essentially the late 19th century as a result of overhunting and diseases brought in by shepherds and so forth. And this picture is from 1933, and here's a Yosemite Park ranger looking at the sheep carcass. Then moving south, actually after John Muir left the artists to paint Mount Lyell, he decided to go south and climb Mount Ritter, which is the highest mountain in the region. And the Ritter Range itself has a number of small glaciers on it. This is typical for what they look like. It's a very rugged kind of mountain range. It has a different character than much of the High Sierra because the bedrock is metavolcanic rather than granite. And there's lots of little glaciers like this that are confined to these basins that are facing northward and hence protected from the direct rays of the sun. And these sorts of glaciers are scattered around the Ritter Range. Here's a picture of Banner Peak. And a lot of these little patches here are actually actively flowing ice, and you know they're actively flowing because there's crevasses in them that are opened up by the flow. And then moving south along the Sierra Crest, we get to the largest of the Sierra Nevada glaciers, which is the Palisade Glacier. It's really quite small too. It's only about a kilometer and a half long, and it sits on the northeast flank of the Palisade Crest, which is a fairly rugged mountain spire or mountain ridge. And you can see there's actually about 5 or 6 glaciers. This is the largest by far, but there's 5 or 6 glaciers along the Palisade Crest here. And you can actually see them from US 395 if you go to Big Pine. It's a spectacular place in Owens Valley. And then if you go further south, there's to the west of the main Sierra Crest, there's a number of smaller glaciers that are hanging out in basins like this one. This is the Cahuilla Peaks Ridge. And again, it's a north-facing line of peaks that's got in its lee some residual ice masses that are protected from the strongest rays of the sun by virtue of the topographic shading and the slope being away from the sun. And that's pretty much it for glaciers in California. Okay, now there's a related feature that I'll just mention that's almost pervasive in alpine landscapes, which is this sort of feature here. This is a picture taken in Ionian Basin in the Kings Canyon Park High Country. This, for scale, the relief here is about 2,500 feet. So this is a pretty big rocky mountain. And look at this feature here. There's this rubble-covered pile of stuff that actually is it's slowly flowing down slope like this, and it has a fairly steep front like that. So as it slowly flows forward, that's hard to say. As it slowly flows forward, it drops rock material off the front like so. And this thing is called a rock glacier. If you look at it from above, it has a very tongue-type form. And these things are all over the High Sierra. There's literally thousands of them. And what this is essentially this is the carcass of a glacier. It used to be a regular glacier, but as the climate warmed and these glaciers started melting back, the flux of sediment off the hill slopes above succeeded in mantling the ice to the extent that there was effective thermal insulation of the underlying ice, so the rest of the ice underneath never melted away. So this is really the carcass of an old glacier. It has an ice core which allows it to slowly creep forward, but it isn't really gaining any new mass. Okay. All right. Oh, yeah, sure. If you were to drill down through them, which has been done in a few places, if you drill down through them, they usually have a solid ice core. All right, so much for our tour of current glaciers in California. And now let's think about the longer time scale. Here's a map showing the extent of glaciation in the High Sierra, the High Southern Sierra, during its maximum during the ice ages. And here's the Central Valley over here, just east of Visalia. Here's Owens Valley over here. So this is a transect across the Sierra. Here's the outline of Sequoia and Kings Canyon parks. And what's shown in shading here is the extent of ice during the last glacial maximum, the most extensive glaciation of the past. And as you can see, there was a huge amount of ice here. It was the really high country was almost entirely covered in ice, except for a few peaks that would stick out above the ice. And then there were tongues of ice that went down the major canyons, like here down the Kings River, there down the Middle Fork of the Kings, here down the Kern River, and so forth. And to put it in perspective, the last 10,000 years of Earth history has been relatively warm. This is the period in which modern civilization arose and so forth. And this last 10,000 years is really uncharacteristic. It's much warmer than the planet has been for most of the last 2.5 million years. In fact, only about 10% of the last 2.5 million years has been anywhere near that warm. So when you think about California, if we take the million-year perspective, California has actually been on average somewhere between this state of ice and our current state of having almost no ice at all. So California has been a much icier place. And the landscape, of course, reflects the legacy of this in a lot of different ways, which we'll come and talk about a little bit later. But I'm going to take a little detour here. Of course, this ice age glaciation of the Sierra was happening at the same time as expanded glaciation around the globe. So there was much bigger versions of the Antarctic ice sheet and the Greenland ice sheet present. And of course, there were big ice sheets on Scandinavia and North America, both. So in the eastern part of North America, the ice sheets had advanced southward to about New York City. Long Island is simply a deposit at the edge of the old ice sheet. In the central part, the fertile plains of the upper Midwest in the United States and southern Canada are deposits of glacier transported debris. And in the west, there was glaciation that covered the Cordillera, the Canadian Rockies, and the BC Coast Ranges and the Cascades. And a tongue of ice had flowed south and ground out the Puget Sound, where now Seattle sits, surrounded by lakes and water that give you great views across to the mountains. And it's important to think about these giant ice sheets, which I'll just call the polar ice sheets for simplicity, both back then and in the present, for two main reasons. First of all, because they provide important feedbacks on climate change. If you cool the climate, that will cause an expansion of these polar ice sheets, which, because they're reflective, will cause a further cooling of the planet because it'll reflect more of the sun's energy back to space. So during the last glacial maximum, there was about a 2 watt per meter squared reduction in the absorbed sunlight at the surface, which is as a result of the expansion of the ice sheets, which is about 1% reduction of all the sunlight that's absorbed. Secondly, as the big ice sheets grow and shrink, that water has to be coming from somewhere. And where it's coming from, of course, is the ocean. So when big ice sheets grow on the planet, sea level is reduced. During the last glacial maximum, at the time there was this sort of glaciation on the High Sierra, sea level was reduced by about 120 meters, or a bit over 400 feet. So there was shorelines all around the world were farther out. And currently, if we look at all the glaciers we have on the planet, which is primarily the Antarctic and Greenland ice sheets, currently there's about 80 meters of sea level equivalent in them. So if the climate warms to the extent that all that continental ice is melted, sea level will rise by something like 260 feet, which would, of course, drown most of the cities of the world. And now from the California perspective, of course, this connection between the polar ice sheets and sea level gives us a very direct connection between the polar ice sheets and California, because the coastal setting of California is really seen here in a typical view on the Big Sur coast. The coastal setting of California is really just one aspect of this interaction between the ice sheets and the sea level. So here's a classic sort of view on the Big Sur coast. There's the ocean, and there's often these wave-cut cliffs, and then the topography rising above, and the topography is often interrupted by these more gently sloped features like so. So remember, during the peak of the last ice age, which was about 20,000 years ago, sea level was lower by 120 meters. What that means, of course, is that the San Francisco Bay was a terrestrial watershed. It was not a marine feature at all. The San Francisco Bay is a relatively recent feature. It's essentially a drowned landscape, much in the same way that, say, Chesapeake Bay on the eastern shore of the US is a drowned valley. Tamales Bay is another great example. When sea level was lower because the big ice sheets had grown, the terrestrial processes, the river erosion had sliced a long linear valley through between what's now Point Reyes and the mainland. And then as sea level rose and drowned that, we got this phenomenal sort of linear odd bay that's Tamales Bay. And it means that the erosion that's responsible for forming these sea cliffs has been going on basically just since sea level rose to its current level, which was about 6,000 years ago. So whenever we think about coastal erosion, it's always important to recognize we're looking at about 6,000 years of landscape change here. And then the pulsations of sea level over time, in conjunction with the tectonic uplift of the landscape, gives rise to these more gently sloped features here, which are marine terraces. So right now, the waves are cutting into the cliff here. In the last 6,000 years, they scraped off a platform over here that you can sort of envision because there's rocks sticking out here. And then as uplift proceeds and sea level goes down as glaciers grow, eventually this feature will be uplifted and become one of these kind of broad features. And these things are really important in the California landscape too. The Coast Highway takes advantage of them in many places. So that's the past, the effects of sea level in the past. And then what about the future? Of course, there's a lot of discussion now about global warming, the warming of the climate on the planetary scale. And global warming is expected to lead to sea level rise for two reasons. One is that the ocean simply expands thermally. The other is that the warming will cause melting of the polar ice sheets, and that will cause sea level to rise. And it's expected that the melt of the Greenland ice sheet alone will cause about 3 meters of sea level rise in the next 1,000 years. So when we talk about really significant sea level rises from melting of the polar ice sheets. We're talking about a time scale of half a millennium to a millennium in the future. It's nothing that you or I are really going to see the impact of. But there is, I mean, there's an interesting connection to California, of course, which is that one of the main reasons global warming is a concern is that it's being driven by carbon dioxide concentration increases in the atmosphere, which are a result of fossil fuel burning. So as has been discussed in the legislature of California, for example, California has a role in emitting carbon dioxide to the atmosphere, which is part of this change here. This is looking at the last 1,000 years, what the carbon dioxide concentration in the atmosphere has been, and it was kind of trucking along without much change at about 280 parts per million for the last millennium. And then when the Industrial Revolution really kicked in, there was a rise in the carbon dioxide concentration like so. Let's just ask, I mean, you get the impression from the popular media that the scientific status of the debate on global warming is not really resolved. And that's true to a certain extent. The last several years have really seen a fairly profound consolidation of the evidence about global warming. I actually had an article in the San Francisco Chronicle a little while ago that talked about this. This was from October 9. I don't know if anybody saw it. I'm not responsible for the graphic. I thought the graphic was cute, though. And what I said in this article is that, you know, if you look at the technical literature from the last several years, it's quite clear that the real serious scientific debate about global warming has ended. There's no real question that there are anthropogenic changes of the atmosphere that are having and will have a quantitatively significant warming effect on the climate. And it's not the focus of this talk, so I won't go into any detail, but it's basically that, you know, we now can observe a warming of the planet in all its different components, especially the ocean, that shows the planet is absorbing heat and warming. We have validation that the climate models are accurate by looking at past climates. And we know now with certainty that the ocean and the biosphere are not going to rescue us by somehow sucking this carbon dioxide back in at the time scale that's needed to. But note, so what was resolved here is that we know there's a warming influence that's quantitatively significant due to anthropogenic fossil fuel burning. But that's not the same as saying we know that we can predict the climate. There's also natural variability that happens that's really poorly understood. So the warming influence is going to be in addition to or interacting with whatever other variability would take place, which means the warming could be a lot worse or it could be a lot less than the anthropogenic impact itself would give. The most important point about global warming is that the warming that's happened to date that's attributable to human activity is really quite trivial quantitatively. It's something like 0.2 to 0.3 degrees centigrade. So when we talk about global warming due to CO2, due to fossil fuel burning, the importance really is from the future perspective, because we're now at about a 30% increase of CO2 in the atmosphere over its natural level. And where we're headed in about 400 years, if we keep burning fossil fuels, where we're headed is to increase that CO2 level by over 7 times the natural level. So, I mean, now we've just increased it by 30% at this point, and where we're headed is to have a 7-fold increase, almost an order of magnitude increase. So it's really a concern for the future. And of course, the sea level impact is one of the major concerns that brings us back to glaciers. So here's, for example, a prediction of how the Greenland ice sheet, shown here as a topographic map, will shrink under different warming scenarios. And to summarize this, I could say this is the Greenland ice sheet now covers all of the island of Greenland except for a few fringe areas. And this is the prediction of what it's going to be about, well, it depends on how much CO2 is put in the atmosphere, but this would be where it is in about 700 years if fossil fuel burning continues and then stabilized at about 1,000 ppm. And there will be huge impacts of that on coastal communities, as the lesson of Hurricane Katrina, of course, is that the sea really matters in conjunction with storms more than anything else. There's also, just when you start talking about reducing the Greenland ice sheet by 3 meters of sea level equivalent, vast areas that are low-lying, like southern Louisiana and southern Florida, will be quite vulnerable. Not to mention low-lying islands that will be completely destroyed. And one of the things about glaciers, the polar glaciers, that's really interesting is that just in the last few years, we've actually been able to measure what's happening in the polar ice sheets with much more completeness and certainty than ever before. And we can see that in response to the active warming, there's a little bit of growth of the interior of these ice sheets because of increased snowfall, but the edges are melting back much more rapidly. And in some cases, there's interesting dynamical connections where the melt is causing increased flow rate, and that's what's shown here. And that increased flow rate is shrinking the ice sheet. This is, you can't see it too well, but here's one of the main outlets of the Greenland ice sheet, and the colors show you flow rate. And from the early 1990s to the year 2000, there was an increase of about 40% in the flow rate of this major outlet of the Greenland ice sheet. So there's huge connections, or the huge impacts of California's fossil fuel burning, in conjunction, of course, with everybody else's, on the polar ice sheets and thence on sea level, and hence back on California. I think the issues of, say, liability aside, for California itself, the bay shore is vulnerable to sea level rise. The ports of Los Angeles and Oakland are vulnerable to sea level rise. A lot of small communities in the coastal zone, like Bolinas and Bodega, would be vulnerable to sea level rise. But overall, California is going to have less problem with sea level rise than most places, for the simple reason that the topography in California near the ocean is quite steep. Okay, so that's currently what's happening to the polar ice sheets. They're thickening a little bit in the middle, and they're retreating and thinning on the edges. Let's return to the Alpine glaciers. If you look at the last 150 years, Alpine glaciers have been retreating worldwide, and this is famously documented in the Alps because there were very good paintings made and etchings made showing where the glaciers had slipped down into valleys in the Alps, like the Rhone Glacier at the head of the Rhone River. And then in the last 150 years, they've really melted back. And this is the case in California too. Here's pictures of the Lyell Glacier. This is Mount Lyell in Yosemite Park, and this picture was taken in the early 1900s. And here's the west lobe and the east lobe of the Lyell Glacier. This was a picture taken in year 2000. You can see there's been retreat of the glacier, especially on the east lobe here. And this is a response to climate warming. There's really no question, if you look around the world, that most of the glacier retreat that's happening in the mountain ranges is due to climate warming. Here's a map view of that, and these images are due to Andrew Fountain, a professor at Portland State. And here's the outline of the glacier in the 1880s, the 1883 outline on Mount Lyell. And then here, this next outline, that was 1944, right there. And then this final outline, that's its current configuration, year 2003, almost current. So it's been steadily retreating, especially the east lobe is almost gone, actually. The west lobe doesn't seem to be doing too bad, but is retreating. So when John Muir found these glaciers, they were definitely bigger. And I said this warming is due to retreat. I'm sorry, the retreat is due to warming. What a logical problem there, sorry. And here's the well-known curve that's been compiled from instrumental records of how the planet has warmed. And over the last 150 years, this period in the mid-19th century, that was the Little Ice Age, the so-called Little Ice Age, a cold period. And this is when the glaciers in the Sierra had sort of reached their maxima, and they were depositing those rubbly ridges, like I showed you in the picture from Mount Conness. And then there was warming through the early 20th century, kind of a pause in the warming, and then warming in the last 20 to 30 years. And remember from that map I just showed you of the Lyell Glacier, there was a lot of retreat between 1944 and 1887. So this warming in here caused a significant retreat, and then this warming here has continued to cause retreat. So when we talk about global warming and the anthropogenic impacts, people always want me to talk about glaciers retreating in response. There's a very subtle thing, perhaps, to appreciate here, but very important, which is that as far as anybody can tell, this warming here had nothing to do with the Industrial Revolution, had nothing to do with carbon dioxide in the atmosphere. It probably was a result of brightening of the sun. And that caused quite a bit of glacier retreat. And it's only this warming in the last 20 to 30 years that's really demonstrably due to the increased carbon dioxide content in the atmosphere. Back here, but at this point, the increase of carbon dioxide in the atmosphere just wasn't quantitatively significant enough to do it. And there's also a lag time. Once you put carbon dioxide in the atmosphere, it takes about a century for the climate to fully warm and come into equilibrium with that. So the glaciers are retreating. This part probably due to human influence, this part almost certainly not. So it's a complicated thing. Both factors are in there. But we really have a much better understanding of this than we did even 5 years ago. So now, when am I supposed to end?
Another 5 minutes?
Another 5 minutes? Okay. So now thinking about John Muir again, of course, John Muir was one of the people who really understood that the Sierra Nevada bears an imprint of its Pleistocene glacial history. And that imprint, that legacy, the Pleistocene legacy, is apparent from a number of very well-known sorts of features that were explicated by 19th century scholars. Here's a conceptual diagram that William Morris Davis put together. Here's a view of a landscape before glaciation. So that's just rivers and debris flows and so forth doing the landscape evolution. Then you glaciate it, and what you get out of it is a landscape that looks like this. It's much more rugged. There's basins called cirques carved into the headwaters of the valleys. Then there's jagged peaks. There's deep troughs where the main glaciers, the high discharge outlet glaciers, came barreling through, and they cut off the tributary valleys and leave them high and dry, and or leave them high. And there's often waterfalls that join the two. And all of these features are seen in the Sierra to some extent. There's a scene in one of the headwaters basins, this big set of jagged peaks here was undercut by glaciers eating their way headward. This is a pretty typical one of these cirque basins. This is, there's lakes here. There's really steep cliffs at the head of the valley. This is the drainage divide up here. And one of the remarkable things about glaciers is that they can do a lot of erosion right near the drainage divide, much more so than rivers can. So one of the most characteristic features of landscapes that have been altered by glaciation is you get these deep scoops out of the drainage divides. And these are the cirque basins. And of course, there's lakes left behind by scouring of the bedrock and by damming by debris. This is a typical broad, high-altitude basin. There's peaks up here, little lakes scattered around, and lots of bare bedrock exposed. And then finally, the deep troughs, of which, of course, the Yosemite Valley, which is the Canyon of the Merced, is the most famous. But here's one that I like better. This is the Middle Fork of the Kings River. And that's this deep, widened valley with very steep, glacially sculpted sides. So why does this Pleistocene legacy matter? And I'll just say a few things about that. The first reason it matters is simply an aesthetic reason. The aesthetics of the High Sierra, it's due to a combination of erosional processes and the rock mass properties. The Sierra is this, you can think of it as this big westward tilted block of granite. And it was first etched very extensively by river networks. And then in the Pleistocene, the glaciers came along and sort of did the finishing job. And quantitatively, the erosion the glaciers did is not really all that well known. It was probably quite large in a few places, like in some of these deep canyons. But in most of the places in the highlands in the Sierra, it was probably a fairly superficial sort of job of finishing. But nonetheless, that superficial finishing that chisels the peaks and makes these lake basins really is a lot of the reason for the unique aesthetics of the Sierra. Why do aesthetics matter? Well, first of all, they're just, we're human and we like looking at things that are aesthetically inspiring. There's recreational reasons why it matters. There's certainly, if you look at the movement of people around California, how they recreate, to go, say, fishing in the mountains or touring in the mountains or hiking in the mountains, the aesthetics of the mountain range is a big draw. And then, of course, because people go to those landscapes, that influences the water quality and so forth. The introduction of fish in those landscapes affects the lake ecosystems and so forth. Another reason it matters, the aesthetics matter, is that this landscape was really one of the primary motivators for the modern environmental movement, or the inspirations for the modern environmental movement politically. And that's had all kinds of ripple effects on the waterscapes around the world in California. It was the environmental movement really started with a focus on these sort of natural treasures, which of course is reflected in our national park system with its focus on the Yosemites and the Yellowstones and the glaciers, the glacier national parks. And it's only later that the environmental movement expanded to encompass concepts like clean air and clean water as sort of general pervasive values. And only in the last really 10 to 15 years that the idea of functioning watersheds and healthy watersheds became a prominent part of the environmental movement. But it all originated in this appreciation for these sorts of landscapes. And if any of you have not really read John Muir, you should. It's beautiful, beautiful writing. And for example, one of the main environmental organizations, of course, is the Sierra Club. There's a reason it's called the Sierra Club. It's because it got its start to protect the Sierra. And here's one of our cliches. This is one of the ultimate environmental cliches, right? Here's our guy, John Muir, standing with Teddy Roosevelt on Glacier Point in Yosemite. And in the background is the Yosemite Valley, which is, it's essentially a river-carved canyon in this very unique kind of bedrock, but then it had a glacial finishing touch put on it that's absolutely spectacular, with the formation of the waterfalls and probably a deepening of the valley by about 20 to 30% and a widening of the valley. And lest you don't think that's important to a lot of people in the state, well, don't forget this. Here's the California Quarter. And what was chosen for it, of course, I guess everybody could agree that this was a good legacy of California. It's not necessarily the biggest impact California has had on the world, but it's one everybody could agree was good. So there's John Muir. And here's Half Dome, which is a granite dome that bears a lot of it, or it owes a lot of its form to the properties of the rock mass. But it also is indebted to the deep scouring that the glacier on its north side did. And then there was a cirque glacier sitting right here on its north side that ate its way backward and made this unique kind of steep cliff on the north side of Half Dome that John Muir is admiring. Then, of course, speaking of aesthetics, our governor had to come and ruin it by slapping a bird right in the middle. It's like, is the bird going to go for John Muir's nose? How did it come out of the half dome? I mean, there's just no sense for spacing. Okay. Other aesthetic things, of course, there's a lot of Hollywood. For example, if they wanted a nice mountain backdrop to a western, they would go to Owens Valley, and the jagged high Sierra would be in the background. And then finally, let me just say one more thing. There's also enormous legacy effects on the hydrology of the state. And if you think about, here's a watershed in the high Sierra that's been glacially excavated. This is the North Palisade, and down here is the middle fork of the Kings River. And there's about 6,000 feet of relief here. If you can see very closely, there's a switchback trail going up here. That's this part of this horrendous rise that you have to do to get up to Bishop Pass out of the middle fork of the Kings. So because the glaciers scoured this whole area, the distribution of elevations, or think about it as the frequency distribution of elevations in the Sierra Nevada, was altered by the glaciation. In some places it was a significant alteration. In other places it was pretty superficial. But think about how important that is for things like the timing of snowmelt coming out of the mountains. The timing of snowmelt coming out of the mountains is, as the snowmelt proceeds upward in elevations, it's reflecting that frequency distribution of elevations, which itself is a product of glacial adjustment of what the watersheds had done. Also, in terms of hydrology, one that's certainly significant quantitatively is that the surface properties of the watersheds have been altered by the fact that the glaciers really scoured the terrain and left a lot of vast areas without any soil at all, without any porous cover. So here's a classic sort of place with bare rock bosses, bare rock over here. And then in the only places you have vegetation are places where there's little bits of ground up rock material in between. So now if you think about how snowmelt and how rainstorms get converted to runoff in a river, this sort of surface property is really profoundly important. If you have bare rock that doesn't allow much infiltration, you get a very rapid transmission of snowmelt and so forth, and precipitation events to the rivers. And that then affects the discharge hydrographs in the rivers profoundly. And then finally, the last point, the glaciers have scoured out, one of their primary impacts is to scour out the valleys so that the longitudinal profile, the elevation changes as you go down valley, are really quite different from what rivers do. And there's the glaciers scour out deep basins that then become filled with sediment and are now sections of meandering river with an ecosystem that's unique to slow-flowing rivers. And then between them, there are places like this that are cascades. So the morphologies of the river channels, the ecosystem along the river is all profoundly affected by the glacial imprint on the longitudinal profiles. And in the extreme case, of course, there's series of lakes like this series of lakes. And of course, one thing that happens with these lakes is that sediment can't get out of these basins. There's rock material coming down the hill slopes, depositing in these fans on the side. And these basins are essentially acting like sediment traps. So on the long time scale, this rock material isn't going to get out of the mountains until the next time glaciation grows to the extent that it has these big tongues of ice way down Yosemite Valley and Kings Canyon. So when you look at, say, the sediment fill in the Central Valley of California, our agricultural heartland, if you want to understand why it's built up as it is, you have to understand the glacial history too. I'm going to end abruptly there because I'm out of time and we want some discussion.
We have enough time for questions.
Yes?
There's something quantitative I don't understand. You say that the temperatures have risen only 0.2 of a degree centigrade in the past century. And the adiabatic lapse rate is 2 degrees centigrade per 1,000 feet. So that 0.2 of a degree centigrade would be equivalent to lowering the mountains by 100 feet. In other words, if you could raise a mountain to Sierra Nevada by 100 feet, could we return to the 19th century level of glaciation? There's something I'm missing here, but I don't know what it is.
Okay, well, I mean, one thing that's missing is, of course, you cannot raise the Sierra by 100 feet. But what I said was the anthropogenic part of the warming of the last 150 years was only 0.2 to 0.3 degrees centigrade. The total warming of the last 150 years as a global average is about 0.7 to about 0.7 degrees centigrade. So the anthropogenic part of it, this part that's happened only in the last few decades, is less than half of that total warming we've seen. Okay, so that was one thing. So the global average rise was about 2.5 times that anthropogenic change. Okay, are you with me so far? Secondly, that's the global average, and what happens locally can be, really quite different. We honestly don't have a really good sense for how temperatures in the Sierra changed over the last 150 years, other than the glaciers are retreating, and that really suggests it got warmer. And if you want to look at what's controlling the glaciers, there's two things to appreciate on the physical side. One is that it's really summertime temperatures that matter the most. You can make the winter colder or warmer, and it doesn't have a whole lot of impact. It's the summertime temperatures when melt is happening. So there's a seasonal aspect to it that we really know even less about. And then secondly, just the physics of the melt process is such that you get a lot more melt with a very little bit of warming. That's just the way it is, because these let's see, can I encapsulate that in a better way? Well, I guess not. Melt happens rapidly compared to snowfall. Let's say typical melt rates are meters per year, whereas typical precipitation rates are fractions of a meter per year. And that melt is happening in a relatively short intervals in the warm season. And if you climatically raise the mean temperature by a few tenths of a degree centigrade, that can, we just know observationally, that can give rise to a large increase in the total number of days over which melt occurs, and you couple that with the fact that the melt rates are fundamentally rapid, and you get a large impact on the glaciers. It's a really interesting thing. If you, the broadest sort of argument about it that's worth looking at is that if you look at the mountain ranges around the world outside of the polar regions, you go to all the mountain ranges of the mid-latitudes and the tropics, every single one of them has their glaciers on average retreating. There's a few glaciers that are advancing because of peculiarities of what their basins are like and what snowfall is doing. But if you go to the coastal Alaska, the Canadian Rockies, the American Cordillera, the Andes, the Southern Alps of New Zealand, Kilimanjaro, the Ruwenzori's, the Alps, the Himalaya, there are all those places the glaciers are retreating. And there's a glaciologist at Utrecht named Hans Erlemunds published an analysis in Science in fall of 2004 that shows that the best way to explain this, if you use models for what controls the mass of glaciers, the way to explain it is about a 0.6 to 0.7 degrees centigrade warming on average, which not coincidentally is about what we think happened from the instrumental record.
So if we could raise the Sierra by 400 feet, we could return to 19.
Yeah, that's quite a job. Yeah. But well, okay, never mind. Sorry.
Up in Montana, there has been quite a bit of press about the glaciers in Glacier National Park, which are going to disappear, and Glacier is going to be glacier-free in 30 years. And there's actually been quite a bit of consciousness raising. And I've heard about, quite a bit in the North Cascades as well. Not so much about the Sierra. Are these glaciers a little bit more buffered because of their spot, or are they so few and far?
They are buffered from the human eye because they are out of sight. They're really small compared to even, well, certainly compared to the North Cascades. The North Cascades glaciation is fairly extensive, especially if you look at the big volcanoes. It's approaching Alps-type glaciation. The ones in Montana are certainly a lot bigger than the ones in the Sierra. They're also, though, kind of hanging out just at the edge of viability. So it's mostly a combination of the fact that the Sierran glaciers are really, really small, and they're really largely out of public view. I mean, I love the Sierra dearly and love these little glaciers, but you're not gonna get anybody really excited about the retreat of something that looks like that, right?
Are there any decent historical photo comparisons that show the retreat of any of these?
You obviously were taking a little snooze, which is something that I can certainly sympathize with. I do the same thing. Let me show you that for the Lyell Glacier, actually for several of these glaciers, there are good photo comparisons. Here's the Lyell Glacier. Ah, good. Oh, Nari, I'll do you first.
I have a comment. I think historically we have been trained to think in terms of the present. Most of our engineering issues traditionally has been restricted to 50 years and 100 years. But one thing that has happened in the last 20, 30 years, because of the environmental movement which was started by Muir and then the environmental impact statements and so forth, is that our time scale for trying to understand and forecast these consequences has tremendously increased. For example, for radioactive waste disposal, our time scale has started with increasing to 10,000 years for Yucca Mountain. Now the National Academy of Sciences came in and extended to 1,000,000 years. So suddenly, as we try to look at environmental consequences, we are now beginning to get worried about future generations and leaving this planet in as nice a state as possible for future generations without our meddling with it too much. There are natural things that will happen, we cannot avoid it. So when our time scale increases to, from normal engineering scale of decades to centuries to 10,000 years, then if you look back 10,000 years, the whole, the Earth was a very different place 10,000 years ago.
Yeah, certainly.
And so then, although, as you say, they are all dinky little features, who bothers about glaciers in California? But the imprints of the glaciers in California, the topography and so forth, which has happened because of the glaciers, we cannot overlook. And they have some implication. We exactly do not know what it is for the future, but we do have to think about them. That's where the importance seems to come, that we need to think about it, not only from the present. In fact, I have read somewhere that between 10,000 years before present and about 7,000 years before present, for over 3,000 years, there were no glaciers in the Sierra. And then it started afterwards.
Yeah, that's right. John Muir was particularly excited when he discovered glaciers in the High Sierra because he thought that they were direct remnants of the Ice Age glaciers that had helped scour the beautiful landscapes that he was enjoying and describing. But it's pretty clear that the early to mid part of the Holocene, that's the last 10,000 years of relatively warm climate, the early to mid parts of that were actually warmer than than present. And there probably were no glaciers at all in the Sierra or in most of the Rockies. There's places in coastal Alaska where glaciers are now retreating, exposing landscapes in which you can find pieces of wood, and you can radiocarbon date them and discover that 5,000 years ago there was a Douglas fir forest covering a valley that has, in the modern recording period, been glaciated until now. So yeah, that's certainly true. As for the longer timescale perspective, I just agree with you that it's, I think the comment I'd add to it is that, you know, the notion of global warming as a result of human activities, which is one that is certainly, I think, the science is solid enough that it ought to be of major concern to everybody. But that's you know, drawn a lot of attention to things like response to climate change, and whether civil engineers have properly designed structures, because, you know, the peaks or the tails of the distributions of floods will change as you go to a new climate state. But I think one thing that needs to be discussed more is that the anthropogenic impacts on climate are happening in conjunction with and in interaction with natural climate change that's caused by changes in the variability of the sun's brightness, for example, changes in the frequency of volcanic eruptions. And I think what we need to have a broader perspective where we think about the climate as being changeable. It's not just the way it's been and then warming in the future. It's hugely changeable. And one thing that I said is that when I said the scientific debate about global warming is over. And what I think that's true, and what I meant is we now are sure that there is a quantitatively significant warming impact of anthropogenic changes to atmospheric composition. But that's going to happen on top of and in interaction with whatever other things are going on. It could be that the sun is going to dim for us next century, and in fact, the whole global warming problem will be a non-problem. It's also equally possible that the sun is going to get a little bit brighter, and the warming that's going to happen is going to be much worse than predicted. So we have to be thinking about that too, and there's not a lot of understanding of the natural climate change. But I should also point out, of course, that on the time scale of a few centuries, let's say 400 to 500 years, if we continue burning fossil fuels as on the trajectory that we are, we're really going to return the atmosphere to a state that it last had in the Cretaceous 60 million years ago, when dinosaurs were frolicking joyously in the polar regions. And I mean, it's again, as I think I said this, but maybe didn't emphasize it enough, that global warming is a problem because of what it implies for the future. The actual changes that have happened so far due to the human impact are really quite almost trivial, although it depends on where you are.
That brings us to a very interesting statement about modern science. All said and done, most of our science is historical. That is, we have been able to collect data and try to say something about what might have happened in the past. Our data sets are very good reasonably good for interpolation. But when you want to extrapolate into the future, then there are so many uncertainties that the sun's luminosity could change or something. Those are so far beyond our control that the only thing possibly, all these techniques that we have now, various forms of looking at these things, probably tells us how to sense danger before it happens, imminent danger. And rather than trying to predict these things, try to learn to adapt ourselves to how best we may live with this. That may not be a very easy thing to do.
Mm-hmm. Yeah, I think that it also, the historical earth sciences give us a perspective on what the range of natural climate variability is and the style, which is quite important. So one of the most interesting results of analyses of climate history from the ice cores in particular, but also marine cores and so forth, is that there are there have in the past been very rapid climate changes of large magnitude. And these were things that were not at all predicted by climate models that involved increases of temperature of 10 degrees centigrade in a decade that then persisted for 1,000 years. And the climate science is actually still very much, the big questions, the really big questions in climate science are driven by these observations from the historical record more than anything else. Climate models don't predict that sort of behavior, and people are trying hard to make their climate models predict it. So it's a really, I don't know, it's a great example of the value of historical science, which really has its goals, the goals, or the activities of historical science are not necessarily hypothesis-driven, but it's more like exploration. Just as John Muir was exploring the High Sierra and discovering these little glaciers, it's still important to explore into the past without necessarily knowing what you're going to discover. That's as philosophical as I ever get.
Any more questions?
Yes?
I'd like to know a little bit about you personally, like how often you travel, and what you do about hiking, and how do you keep yourself out of the crevasses. A little bit about your clothing, maybe, and where you live when you're out.
Well, that's a pretty big question, actually. Maybe we should turn on the lights if we're done with this. There. Well, so how much do I travel? I don't travel as much as you might think because I've got a job. Despite what people think, being a professor at a university is a job. And I've got projects and students and so forth that I have to deal with. Mind you, I do it voluntarily. It's a great job. I've got professional trips and I've got pleasure trips but I don't really necessarily separate pleasure from profession in my mind, because what I do for pleasure involves exploring landscapes that I think about. If I had to classify myself as a scientist, I'd call myself a geomorphologist, somebody who studies the surface of the earth, the processes that shape it, and the landforms. So I think any time I go somewhere, as long as my eyes are open and I'm not in a fog, I'm doing my job. And I use pictures that I get on my pleasure trips in classes, and one of my goals is I'd like to, in a few years, write a book about the Sierra Nevada and the North Cascades. So every time I go on trips, I think about that too. The research trips, it's very much project dependent. I do some work in Antarctica. I've had the pictures I showed you from Taylor Glacier in Antarctica, that involved 2 fairly extensive field excursions to Antarctica, which Andy Bliss, my student sitting back there smirking, was part of. But that's done now. There's no more field work in that, and that's the way I want it to be, because you can't get very much work done on anything except that project when you're down there. It's fun. But that was a couple months at a time. And then in the project I'm just getting started now with Johnny Sanders sitting back there, another student, that's going to have, for me, just a few weeks of field work in the Canadian Rockies. And then for pleasure trips, I've made sure that I take a few weeks every year to go exploring the wilderness in mountains, especially by backpacking. As far as clothing goes, in Antarctica, we wear lots of big clothes. And it's amazing what you can live through if you put on a really thick, well, you put on 5 layers of clothes and then you put on a big parka. And it's amazing. You can and you zip up the hood, so your view on the world is a little tunnel like that, and there's a fur-lined hood. And the wind can be howling and it can be snowing, and you can just actually be quite comfortable just sitting there. And then, of course, places like the High Sierra, it's, in midsummer, hiking, I just wear shorts and a t-shirt. Does that answer your question? I could.
What about the crevasses then?
Oh, crevasses? I avoid them. I'm not an ice climber. I think glaciers are actually extremely dangerous places, and I have no intention of dropping down into crevasses to do research on the ice that way, and no intention of working in places where it's really a hazard. Yeah, sure.